Hi guys, Dave here, G7IYK. I hope this video is going to be okay. It's not using my usual video setup microphone. I'm just using my phone on a stabilized gimbal, reasonably stable most of the time. Anyway, I thought I'd just do this quick video because I've just recently been a bit naughty and acquired Rigol whatever, DSA815 spectrum analyzer, 9 kilohertz, 1.5 gigahertz. I had the Rigol oscilloscope, which I was really impressed with, and I have to say this spectrum analyzer has surpassed my expectations. It is really nice bit of kit. I've been very impressed with it. I know the upper range is only 1.5 gigahertz, but for kind of what I'm doing, ham bands, amateur, workshop-based radio stuff, it's more than adequate. It's got every single feature you could possibly imagine on it. The particular model I bought, which I would encourage others thinking about buying this model to also get, is the model with the tracking generator. So this is this output here. So basically, if you don't know what a tracking generator does, as the spectrum analyzer sweeps its frequency from wherever you start to wherever you decide to finish, the tracking generator does what it says on the tin and tracks that frequency. The idea being that you can take the RF output from the tracking generator and then put it through, say, a filter or a power amplifier or something you're trying to characterize. So that's basically what I'm going to try and do in this video, which is to characterize one of these little this is a QRP Labs low pass output filter. So it's just an exercise, really. I just sort of show you how I'm doing it. I mean, there's probably different ways of skinning the cat, but this is the way I'm doing it. So this is an output filter. It's a 20 meter filter, so sort of around the 14 megahertz mark, and they're great little filters, and QRP Labs in the US supply them so pretty much globally, and they're really, you couldn't buy the bits to build it, I don't think, or you'd struggle. It's maybe not worth it, but they're really nice, and as is all the stuff from QRP Labs. So anyway, so there we go. So basically I've just set the thing up and I've pressed the preset button over here, which basically sets it up to full span. So it's now running from, it's centered at 750 megahertz. It's running from 1 megahertz to 1.5 gigahertz. You can see that written down the end there, 1 megahertz to 1.5 gigahertz. So that's that, yeah, with a resolution bandwidth of megahertz and a video bandwidth of a megahertz. So that's kind of like a sort of a starting point, as it were. So, and then what I've done is I've connected the tracking generator to the input using a piece of BNC to BNC patch cable, and I've got some adapters here, BNC to the front of the spectrum analyzer. So so the idea is I'm going to go over what I do in order to characterize a filter. But what I'm going to do, the cables I'm going to be using to characterize this filter are not great, which is sort of kind of like where this whole sort of video comes from. I'm just using sort of standard scope leads with pretty thin, wishy-washy sort of, cable on. So I'm expecting them to be a bit lossy, and I'm also expecting them to probably have some sort of some sort of frequency dependent characteristic. So but this cable here should be reasonably okay. It should be fine. It's short and it's reasonably meaty. At this sort of frequency shouldn't be a problem. So the first thing I'm going to do, I mean, I know my filter is 20 meters, so around about 14 meg. So what I'm going to do first is I'm going to set the frequency to sweep from 10 megahertz to start frequency of 10 megahertz. It's a good start, wasn't it? Stop frequency of 30 megahertz. Okay, so that's now running from as it says down here, 10 megahertz to 30 megahertz. The tracking generator is currently off at the moment because this is the tracking generator light, and it's not on. So it's an interesting little feature with the tracking generator. When you press tracking generator button, you get that basically pulls the menu up, but it doesn't actually turn the tracking generator on. You have to turn the tracking generator on here. So if I turn the tracking generator on, now what's happening is it's gone to what looks like a solid line here at approximately minus 20 dBm. If I stick a marker up in the middle, so it's actually at minus sort of 18.99 dBm. And the reason that is because the tracking generator is set to an output level of minus 20 dBm. I mean, the tracking generator on this is good. That's the best way of putting this without making it sound like I'm criticizing it, because I'm not. Tracking generators are quite difficult to achieve. To sweep the tracking generator from sort of 9 kilohertz to 1.5 gigahertz perfectly flat is actually quite tricky. So what Rigol have done here, which I will demonstrate in a minute, which is actually quite cool, is it allows you to the tracking generator has a normalization function, which allows you to sort of flatten any imperfections in the tracking generator. So they flatten the imperfections in the tracking generator in software, and I'll demonstrate that in a moment. Which means you can actually generate a reasonably inexpensive tracking generator in a sub £1,000 spectrum analyzer with known imperfections, but then fix those imperfections using software profiling, which is, you couldn't do on old non-software based spectrum analyzers. So yeah, it's a really powerful feature, and it works really well. So that's as we say, that's pretty flat, and we're kind of a dB and a little bit out, but nothing to worry about. And as I'll show in a minute, it doesn't actually matter. So I'll just stop this little bit of the video, and then what I'm going to do is I'm going to connect up the two scope leads that I just showed, these little fellas, and I'm just going to connect them together. So I'm not going to put the filter in. I'm just going to go like I've done with this cable here, but with the scope leads, just probe tip to probe tip, as it were. Right, I'll be back in a sec. Okie dokie, back again. Dave, G7IYK. So that's what I've done. Probe tip to probe tip, okay, and ground to ground, and then into the two BN, into the one's the tracking generator, one into the input. Right, okay, good. So pretty much the same as before. So again, I've pushed the preset button just to get back to square one again. So I will enter the frequency, same as before. Start frequency 10 megahertz. Sorry if this is a little bit difficult. I'm doing this without my glasses on, so I can't actually see what I'm typing. 30 megahertz. Okay, there we go. Turn the tracking generator on. I'm trying to do it two-handedly. Again, it's set to minus 20. Let's have a marker up. Stick it in. Right, okay. So those cables, as we can see now, check it out. Minus 32 point something. So as we know, the tracking generator is generating minus 20 dBm. We've now got an input level of minus 32 point something. So about a 12 point something dB loss across those cables, and you probably can't see it very well on the camera, but I can see it on the screen. There is a slope to that line. It's not perfectly flat, so those cables are acting, as a very slight filter. That line is ever so slightly on the tilt, which is probably not significant but not ideal. So going back to the tracking generator, so you could do various things to correct that. I mean, not the slope, that would be tricky, but you could correct the level by going to the amplitude menu and maybe adjusting the reference offset, or there's various ways you could adjust that level. So because what we really want, what I want is, because I've got no filter in there, I want that line sitting at 0 dBm, or some reference point. I mean, I prefer 0 dBm, and then when I put my filter in, I can see what the filter does with respect to a line at 0 dBm. So okay, so we've got it in tracking generator mode, and now this is what was to the point I was trying to get to, how you can normalize this tracking generator, which is, I think, a really powerful and cool feature, and it's so easy to do. So you just press the normalize button. Okay, now what happens now is you have to sort of you create a reference, and then you just turn it on. So to create, so it's just sitting there. The normalization is off. The normalized reference level is at 0 dBm, and nothing's changed. So nothing happened there. All I did was move to a different menu. So if we press this reference button here, again, nothing appears to have happened. Every time you press it, it doesn't appear to do anything. But what it's doing is it's now profiling the tracking generator output with the cables in. So if I turn the tracking generator on, the normalization on, excuse me. Now the line shot up to 0 dBm right at the top of the screen up there, and the marker's reading 0 dBm on the money, bang on. So we think, okay, that's great, but maybe I just don't, I don't want it right at the top of the screen, so I'd like to move it down a little bit. So we can now add in the offset reference level, normalization reference level. I think that's what that's supposed to say. So let's say, I don't know, 20 dB. There we go. So now we've got a dead straight line at 0 dBm and nicely positioned about whatever that is, 2 clicks down the screen. So what I'll do now is I won't change anything. I'm just going to go and put the filter in. So I'll do that, and I'll be back in a second. Hi guys, Dave back again, G7IYK. Okay, so all I've done, literally all I've done, is just popped the filter in. So I've popped the little QRP Labs filter, and sure enough, we can see its response. So here we are at round about where we are. 14, 15, 16 megahertz up here, and then you can see it rolling off. So that's great, and it's rolling off to a noise floor of about minus 35, minus 38 dBm. Now there's a couple of ways we can probably improve that, or a couple of ways I believe we can improve it, which is what I tend to do. So because obviously some of the parameters here were generated just as a result of pressing the preset button. So there's two ways really of not so much improving this area of the trace, but getting an improved and cleaner noise floor. So the first thing to look at or to consider, if you go to the amplitude menu, this analyzer has got an input attenuator which has been set automatically to 10 dB. So, but we don't really need an input attenuator, and the effect of adding the input attenuator is that will tend to lift the noise floor, but we don't need a 10 dB attenuator because we know the tracking generator is generating minus 20 dBm. There's no gain in the filter, it's passive, so there can't be more out of the filter than you put in. So we know that the output of the filter can't be any more than minus 20 dBm. It's not a power amplifier, it's just a passive filter. Now this particular analyzer has got a maximum input level of plus 20 dBm, and we're only outputting minus 20, so we're 40 dBm shy of the maximum input power, so we don't need an input attenuator of 10 dB. So if we go to that input attenuator, now we currently got to say the noise floor is what, minus 35-ish. So if I reduce that input attenuator to 0, you'll notice that the noise floor has now dropped to sort of minus 42. So we've improved the noise floor by getting rid of that input attenuator. Now the other thing we could do to improve things slightly is reduce the resolution bandwidth. Now the analyzer set that automatically to 300 kilohertz. Now resolution bandwidth seems to sort of cause quite a lot. Seems to cause a bit of confusion, and it is a tricky thing to get your head round, and it does help if you actually have a spectrum analyzer to sort of experiment. But the way I think about it is, and I can't remember where I saw this term, but it's like the eye of the spectrum analyzer. So we're not sweeping a knife edge from left to right. The analyzer is sweeping frequency from left to right, and it's sampling the response, in this case, of the filter. But it's not a knife edge, it's sweeping a filter, hence resolution bandwidth. It's the bandwidth of that filter, and in the moment the analyzer is set up with a filter bandwidth of 300 kilohertz. So we're sweeping from 10 megahertz to 30 megahertz using a filter which is 300 kilohertz wide. Now the analyzer can only display what it integrates over that bandwidth of that filter. So as power enters the filter, then that power will be integrated and displayed. So clearly, if the filter is wide, then we will end up with more power in the window, in the bandwidth of the filter which is sweeping. So that will give us less resolution, the clues in the name, resolution, bandwidth, and also there will be more power within the window. So if you can imagine, if you're just sweeping the noise floor down here and you've got a wide filter, more noise is in that filter at any one point in time. So the noise floor will rise because you're integrating more power over the filter. So if I increase the resolution bandwidth, make the filter wider and wider, you can see the noise floor is coming up. So that's as far as it will go. That's a megahertz. So that's now a megahertz wide. And the noise floor has sort of come up to basically where we were before we took the input attenuator out. So now the sweep time. The other effect of resolution bandwidth is it affects the resolution and also the sweep time. The sweep time is now 10 milliseconds, which I think is about as fast as I can go. So in order to improve that noise floor and make it appear less noisy, we can just reduce the resolution. So that's where we were to start with. At 300 kilohertz, we got let's go down to. Okay, now we're at 10 kilohertz. Resolution bandwidth of 10 kilohertz. So we were at 200 kilohertz and now at 10 kilohertz. Now the sweep time is now 200 milliseconds. It says that down here. It's quite neat, this analyzer. A lot of analyzers, in my experience, don't display sweep time, but this one does, which is quite nice. But now the noise floor is now, we've now got more resolution and less noise displayed because the filter's narrower. And also the noise floor is dropped to minus 45 dBm. So that was kind of the trace that I was looking for, really. That was what I wanted to get from looking at the filter. So it's nice and clean, it's sweeping reasonably quickly. The noise floor is pretty low. Yeah. So if we pop the marker display back up, so we've got we're going from 14 megahertz here. Or 14.2, there's 14 right on the left hand side of the flat. And if we go to the right hand side of the flat just before it starts to roll off, we're at 16 meg. So it's 2 meg wide, that flat, 14 to 16 meg, and then it rolls off. So if I sit it there just as it's about to roll off and then hit the delta marker, pull that to the right until we hit minus 3 dB. That's minus 3 dB, give or take a bit. So it's basically hit the minus from the flat to the minus 3 dB down point in about 700 kilohertz. And then after that, obviously, it's off to the land of noise. So yeah, I don't know if that was in any way useful, or there are other far more knowledgeable people that can correct me or add to that. Probably. There are, as I pointed out at the start, there are multiple ways of skinning a cat. But for me, with this particular analyzer, which I personally think is excellent, hats off to Rigol. I think they've really pulled a rabbit out of the hat with this one. The way I've been characterizing filters is basically to you can pretty much use any sort of cables you want with this technique, obviously within reason, not bits of wet string or bell wire, but some reasonable cables. Pop those in, connect them together without your filter. Pop on your tracking generator. Use the normalization function to software normalize your tracking generator response to a dead flat line at 0 dBm. Then use the tracking generator offset feature to move the 0 dBm line down a little bit onto a more convenient point on the screen, where it's sort of kind of sitting about here. And then that will give you a pretty good response. And then if you want to improve the noise floor, and you know that your tracking generator is only generating -20, -10, 0 dBm or whatever you've set it to, you can remove any automatically inserted input attenuator to improve your noise floor, and then you can further improve that noise floor and clean up the noise response by reducing the resolution bandwidth to a point where the sweep time is acceptable, and there's no point going so far that the sweep time is so slow that it makes looking at the response difficult. So, you know, I would say for me, 200 100 millisecond sweep time is perfectly good, and it's nice and clean at that point, and you can get a good measure on the noise and see where the noise is sitting. Quite a long way down, as it happens. So yeah, nice little filters and a really nice analyzer for hobby use. If you've got spare change, then and you think you're going to need one, then I don't think personally, I'm not no way affiliated with Rigol or other company. I don't think you're going to find a better analyzer on the market for the money, personally. So anyway, anybody got any comments, civil obviously, then fire away. Cheers, thanks a lot for watching.